This is Dr. Holt. This problem is on a trampoline jumper. Here I have a 72 kilogram trampoline artist jumps vertically upward from the top of a platform with a velocity of 4.5 meters a second. How fast is he going as he lands on the trampoline 2 meters below? And then part B, if the trampoline behaves like a spring constant 5.8 times 10 to the fourth newtons per meter, how far does he depress it? Okay, to set up this problem, we'll do part A first. What I would do would set this right here, the top of the trampoline, right when the person's going to hit, as our kind of our x-coordinate, or where we're going to do our where we're going to do our calculations regarding potential energy from. So what I did, I've already worked most of this problem. Move this out of your way, and let's see, grab all this, move it up so you can see it. I go back to the conservation of mechanical energy. I say the potential energy initial plus kinetic energy initial is equal to PE final plus KE final. So his potential energy in respect to the top surface of the trampoline is going to be his mass times 9.8 times 2, being the distance, because he's starting from right here. Now, since he's launching upward, he also has kinetic energy of 1/2 times his mass times velocity squared, 4.5 squared. All I have to do now is set that up to when he lands on the trampoline and find the velocity. I'm going to do 1/2 times mass times velocity squared. Again, remember, when he lands, he has no potential energy in respect to the top surface. So when I solve that, I get a velocity as 7.7 meters per second. And that's how you're going to do part A. To do part B, now I've set it up a little bit differently. What I'm going to do now is I'm going to set my axis to the bottom of the trampoline when it actually deflects, when the netting deflects. So I know my netting is going to deflect some value of y. I'm going to take all my values now in respect to that. So I go back to his potential energy, which is going to be 72 times 9.8 plus 2 plus the deflection. That's 2 plus y. Now his kinetic energy is not going to change. It's going to be 1/2 times mass times 4.5 squared. When he lands and hits the net, he's going to have a velocity. But when he deflects, to show you down here, as he deflects this trampoline surface, when he gets to the bottom, he's lost all his velocity. He's come to a stop. So I set the potential energy as 1/2 times 5.8 times 10 to the fourth times y squared. This being your spring constant. Now all we have to do now is solve for y. I go ahead and distribute this. I'm going to get a quadratic equation. So all you have to do now is move the y squared over, and you're going to get get a quadratic equation and solve for y. And y now is going to equal to 0.284 meters. And that's all you have to do with this. Here I kind of just broke it down so you could see where everything come from. Again, his potential energy initial, 72 times 9.8 plus 2 plus y. Kinetic energy is just 1/2 times mass times velocity squared, and just set this up as my spring constant, or being the potential energy of the spring. Again, not a bad problem. I just wanted to show you this methodology of how to set up this problem and solve it very effectively. Again, I solved part A first, and then followed around and solved part B.